Okay, I wanted to take a moment just so I could clean up this picture a little bit. So remember what we're trying to do here is we're trying to approximate the signed volume that we get over this blob, where this blob is the image under the transformation T of this lovely rectangle. Okay. So we determined that we needed to approximate the height and we needed to approximate the area of the base, which is the area of the blob. Okay. Now we approximated the height the way we usually did. We just went into denial and pretended that the height was constant and that the height was always the value of the height at that particular point. Okay, so if this point is t of u star v star, we simply plug that into f to get a representative height. Okay. And then we said we could approximate the area of the blob with the area of a parallelogram, where we're going to determine the sides of the parallelogram by taking a vector that's tangent to this curve and scaling it so that it's about the right length, and a vector that's tangent to this curve and scaling it so that it's about the right length. But remember, the blue curves here were just constant v curves. We were holding v constant and letting u change. So the vector that's going to be tangent to that curve is the partial derivative of t with respect to u, evaluated at this point. And we scale that by delta u, because this is giving me the amount that t would change if u changed by 1 unit. If u is changing by that amount, that's what we're going to scale it by. Same thing here. This was a constant u curve, so the vector that's tangent to it is the partial of t with respect to v, and we scale that by delta v. So now I'm going to approximate the area of that blobular subregion with the area of this parallelogram, so I just have to remember how to calculate the area of a parallelogram in 2 space. If you said take the cross product, you're making up math, because in 2 space, there's no such thing as the cross product. Now, I could, if I wanted to, embed this in 3 space and then take the cross product of the corresponding vectors. But I'm already going from the UV plane to the XY plane. I don't want to go to 3 space as well. Okay. And I don't have to. I just have to remember way back when, at the beginning of the semester, we learned how to calculate the area of a parallelogram determined by 2 vectors A and B in 2 space. And what we determined was that the area was the absolute value of the determinant of the matrix we could get by putting A in as the first column and B in as the second column. Okay. Now, we could also put them in as rows. There's actually a reason that we'll get to in a moment about why I want to put these things in as columns. So what I need to do is put these vectors in as the columns of a matrix, calculate the determinant, and then calculate the absolute value. Okay. So the matrix that I'm going to create, I need to figure out what these partial derivatives look like. Well, the partial of t with respect to u is just going to be the partial of x with respect to u, partial of y with respect to u. Remember, t had 2 output variables, x and y, both of which were functions of u and v. Okay. So I'm used to, when I have 2 output variables, my derivatives are going to be a vector with 2 components. It's just now that's a partial derivative. And the partial of t with respect to v is going to be the partial of x with respect to v, partial of y with respect to v. Now I'm writing these as rows because that's what we're used to in writing our vectors. When I create this matrix, though, I'm just going to put them in as the columns of that matrix. So, and this is just the partial derivatives. Don't forget, I'm going to want to scale them by delta u and by delta v. So what I'm going to have then is the matrix that I'm getting is partial x, partial u, evaluated at u star v star, partial y, partial u, evaluated at u star v star, partial x partial v evaluated at u star v star, partial y partial v evaluated at u star v star. Now I've just written the partial derivatives at this point. I haven't yet thrown in that I'm going to scale by delta u and delta v. I'm about to do that. This is incomplete. But I just want to point out this matrix is the derivative of t. So we have seen that derivatives can be a vector. Turns out derivatives can be a matrix. If you have a multidimensional input and a multidimensional output, your derivative is going to be a matrix, where the number of rows and columns are determined by the number of input and output variables that you have. So that's why I'm choosing to put these in as the columns of the matrix rather than the rows of the matrix, so that this part actually corresponds to the derivative of t. For our purposes, we don't really care, because we're just going to care about the determinant and then the absolute value of that, because that's going to be our scaling factor. But you could, in a later class, come across that this is the derivative of t, in which case where you put things matters. Okay? You can't just sort of shuffle the components and say, I've got to have these four elements, but I can put them wherever I want. You can't. Okay. So now let's actually write in the area of this thing. So we had scaled this vector by delta u, and we had scaled this vector by delta v. Okay, so that's the matrix that we have. That's no longer the determinant of t, because I've scaled the two columns. Okay. If I take the determinant of this, let's just say the determinant is, okay, notice I'm going to get delta u times delta v times the partial of x with respect to u at u star v star times the partial of y with respect to v at u star v star minus the delta u times delta v, because those scalars occur in both terms. Oh, and actually, I see what I was doing. I was just factoring that out. I can see in this diagonal product, I'm going to get a delta u, delta v. In this diagonal product, I'm going to get a delta u, delta v. So I'm just going to factor that out. So delta u, delta v times the partial of x with respect to u, partial of y with respect to v, minus the partial of x with respect to v at u star v star times the partial of y with respect to u at u star v star. Okay. But notice what this is the determinant I would have gotten before I had scaled this. Okay. So I'm just getting delta u, delta v times the determinant of the derivative of t. Delta x, delta u, delta y, delta u, delta x, delta v, delta y, delta v. No. Yes. Yes. So notice x and y, what we're going to, correspond to the rows. U and v, what we're mapping from, correspond to the columns. Okay, so that's my determinant, and I'm going to approximate that the area of my region is the area of this parallelogram, which would just be the absolute value of that. Okay. Now, this, of course, is positive. Determinants of matrices could be positive or negative, so I'm going to need to take the absolute value of that. Okay. I'm going to just point out that this thing right here, this determinant of the derivative of t, has a name and some nice notation for it. Okay. So this part right here is what we call the Jacobian. It's the determinant of this derivative, which happens to be the derivative of t. If I want, I can just think of it as the derivative of the matrix containing the partial derivatives in particular places. So I can call that the Jacobian. I can write that as del xy by del uv. Notice x and y were my two output variables, u and v were my two input variables. Of course, I'm going to be evaluating this at a particular point. I've sort of omitted that just because it gets sort of crowded. I want to remember that all of these functions are going to be evaluated at my representative point. But this is just the Jacobian, so I'm going to estimate that the area of the base is the absolute value of the Jacobian, del xy by del uv, evaluated at u star v star, okay, times delta u delta v. So it's the absolute value of the Jacobian that's going to be essentially what we're thinking of as our scaling factor. This I can see, delta u delta v, that's going to become my dA in the uv plane. This right here is the scaling factor. So the absolute value of the Jacobian. Okay, so that takes us through our approximation step. Of course, then what we do is we add all of these things up. So remember, we had chopped things up into a whole bunch of pieces, and so we'd approximated the signed volume over each piece. Now I'm going to add all of those up, and I'm going to get a double Riemann sum. So I'm basically going to have the sum as j goes from 1 to n, as I goes from 1 to m, of f of t of uij star vij star. So this would just be the representative point for the ijth rectangle, times the absolute value of the Jacobian, del xy, del uv, evaluated at that point, uij star vij star, times delta u delta v. But then, when we go to step 4 and we take the limit, so I would have the limit as m and n both go off to infinity. Okay. This is going to become the double integral over our nice region S of f of t of uv, scaling factor dA in the uv plane. And that scaling factor is the absolute value of the Jacobian. So we made an educated guess way back when that we were going to get something like this, and it turns out that is what we get.